start our discussion on chapter 11, which is on frequency response. So the plan is that we're going to briefly go through the concept as to why we want to talk about what is actually frequency response. Why is there a frequency response, and why is it important in electrical systems? And then we're going to talk about, first of all, before we start that, we'll have to talk about the key components we discussed previously when we're not thinking about frequency domain. We're not talking about signal in different frequencies. The response meaning that the input and output relationship, VL, we talk about VL as a function of Vin, and then this would then give me a voltage gain. So this is when we talk about a particular scenario where when there's changes in frequency or change in signal frequency, it does not change the response. But in real case, if you actually think about it, if you consider components that is inside the circuit which actually have frequency response, meaning that under different frequencies, it looks its characteristic or its value, for example, impedance levels, actually changes with frequency. So in real cases, what happens is that this will be a function of frequency. Your output, as the input changes with frequency, your output actually changes with frequency, and the responses actually is a function of frequency. That is why we need to discuss frequency response, meaning that your circuit's input-output relationship is different when input signals are changed under different frequencies. So when one discusses this, we need to, instead of having a simple gain, we typically have something called a transfer function. Rather than a fixed number, it will be a function of frequency. As a function of frequency. So your input-output transfer characteristic, if we talk about transfer characteristic, one is that you look at input swing. Remember when we talk about transfer characteristic, you simply sweep the input DC level. That's called a function of input. But here we're talking about the transfer function as you sweep the input with different frequencies. So it's a function of frequency. Okay, so when one wants to talk about this complicated circuit responses, one of the commonly used tools, these are the tools, this is called the Bode plot or Bode rules. So you want to do a plot to see the response rather than just having the expression, so that you get more an intuitive sense as to what actually happened to the circuits and allow us to actually enter into a more complicated system, especially when we talk about in chapter 12, when there's feedback systems. So when you taking courses, we're not going to cover feedback in this class, but when you're taking courses like analog circuit designs, it would then venture into most of the electronic circuits are actually operated in a feedback mode. If you're having a feedback component, either is negative feedback to stabilize the output or positive feedback to create oscillation. So in feedback control, stability is very important. So then we need to use Bode plots or Bode rules, allow us to get a sense as to when you're injecting signals, which is, for example, noise is a broadband signal. So that means that it has components of every frequencies, mostly all frequency domains, all frequency levels for white noise, for example. So these type of noise would then create instability in the systems. How do you observe that? Through Bode plots or Bode rules. And then we're going to cover that a little bit. And then the second important thing is then, it's called the Miller theory. So this is very important when we have, we call it feed-forward. Capacitor. So this is when we want to discuss these frequency response, most of the component we actually discuss, rather there's two components. Everybody knows that it has frequency domain, frequency dependency for ZC, which is J omega C, and for impedance of inductor, which is J omega L. But in this discussion, we'll probably limit ourselves mostly on the capacitive components, which is mainly happened in lower frequency. In higher frequency, then you need to discuss a component. High frequency circuits, then an inductive component will become, cannot be ignored. Then we need to include that. But in this class, we're typically just going to limit our discussion on the passive, the capacitive component, its impact on the overall circuits. So we're going to focus mostly on capacitors. And then if you have a capacitor which is not standing in ground, meaning that if I have a capacitor, for example, most of the capacitor, the way to think about it is that you have a bucket and you try to charge up the bucket. It's coming, the lowest level is at the ground. So you try to charge up fill up the bucket. So the speed of the movement depends on how fast the bucket rises up. But in feed-forward capacitors, meaning that you would then have a capacitor which it's opposite level, the other side of the potential. So you have V1, V2. So when V1 is moving, then we need to consider Miller capacitance, meaning that when V1 is sinking down further, meaning that you need to pull in more water in order for V1 to rise. Then so if V1 is no longer a constant level, then we need to use what we call the Miller theory to get effective capacitance. This allows us to get something called the effective capacitance. So what it looks like. And this is very, very common because this is some sort of unavoidable control. You can either use that to create effective large capacitance, or this is some parasitic capacitance that exists in your circuits, and you need to deal with this major increase of capacitance, effective capacitance. And then, so in this part, we're going to consider mostly external capacitance you add when you add external capacitance to control your overall frequency response. So you can add these capacitance components to make your circuit function as the way you want. But the other thing we need to think about is that, remember, if you go back to transistors, all the transistors have what we call parasitic capacitance. So we're going to talk about what we call the high frequency model. Of transistors. So one of the key components is that if you think about especially like devices like MOSFET, it's actually constructive capacitors. So there will be parasitic capacitance in transistors. So we're going to talk about what are the parasitic capacitance in transistors. So they are very different because for bipolar junction transistor, there are PN junctions. So PN junctions have diffusion capacitance, depletion capacitance. For MOSFETs, basically parallel plate capacitance. So these capacitance, we want to talk about that in both BJTs and MOSFETs. So and how are they changes when you change device sizes and current biasing conditions? So these are complicated issues we're going to address and then build up small signal models with these parasitic capacitance. And then we're going to talk about something very important, which is called the transit frequency. This basically means that this would then give you something called remember we talked about intrinsic gain of a transistor, meaning that if you're not limited by external circuit, what is the ultimate gain? If you have a most ideal case, for example, a common source amplifier with current source load, ideal current source load, that will give you the maximum gain, the ceiling of your gain. That's called the intrinsic gain. In frequency domain, there's also a boundary, which is the ultimate speed of your transistor. So this would then indicate what we call the intrinsic bandwidth. So what determines what we call the intrinsic bandwidth will then determine mostly by technology nodes. What does it mean? It means that how fast can the transistor push itself, use its own current to fill up its own bucket? How fast can it go? Without external component, the disturbance of its own component. So it's like how fast can you run without all the baggages? So that's your intrinsic speed. So it's technology limited. So we're going to talk about that typically depending on the size of your devices. If you can make it smaller, it's typically allow us to have wider bandwidth. So this would then limit how fast the circuit can be. The limitation of your circuit or the circuit boundaries actually it has to be much smaller than intrinsic bandwidth, because this is when you're running without load. When you add circuits, you're actually putting on additional baggages. Therefore, it must be slightly lower than the ultimate speed. Then fourthly, of course, we're going to talk about frequency response of circuits. So I don't think we're going to go into too complicated structures. We're going to limit ourselves on single-stage amplifiers and probably some little discussion on differential pairs. So we're going to talk about the single-stage amplifier. CSC, GCD. Of course, you can do the bipolar version. We're going to talk about how these, in single-stage amplifier, the effect of having parasitic meaning that within transistor, the effect of parasitic and external when you consider both external capacitors. So we're going to talk about impacts when we add, consider parasitic capacitance and include some external capacitors. Okay, so you consider all these components added and how does it affect your overall response. Especially we want to get, so typically what we want to get in single-stage amplifier, remember what typically you will be asked to analyze is gain input-output resistance. In this case, you want to get your transfer function. That's the most important thing. One is that it's gain at, you need to find out its gain at different level, at different frequency points. This actually indicates that, but just to get a sense as to how it transfers at different frequencies. So maybe F1, different frequencies. And then you want to talk about, you want to get mostly on phases at different frequencies. You should be able to identify that. And lastly, you want to get mostly bandwidth of the circuit. To analyze the bandwidth of the circuit, meaning that you should be able to plot something like this. For example, this will be the gain, voltage gain as a function of frequency, and then we should be able to get these bandwidth. This is the bandwidth of a circuit. So you should be able to plot this and understand these points, be able to extract these points and how to analyze those. So these are the things that we're going to go through, and then after going through this chapter, you should be able to generate this once a circuit is given to you. Okay? Good. So let's go back to what does it mean by frequency response. It basically means that if I have an amplifier, let's say if this is my amplifier, I have an input signal, and I have an output signal. So typically what we think about is that we have a fixed gain between the input and output. But in real cases, what happens is that if I'm giving the same signal, for example, let's just assume that we'll not consider the DC biasing effect. Let's say if this is my input signal. We're only looking at the AC component. So this is my input signal. Typically what happens is that this is the input. And then let's say if I have a circuit with a gain of 2. So what happens is that I assume that if this is my input. Okay, so for a circuit with, let's say, if this is a voltage gain of 2. Okay? So I'm designing a circuit with a gain of 2. What happens is that this is your corresponding result. You expect that, let's say, if I give you let's say if this is 10 millivolt, and my expected output will be 20 millivolt. So I'm assuming that Vout as a function of time will become 20 millivolt sine omega t. So if this is my input, omega 1 simply means that I'm given a specific frequency. Let's say this is 100 millivolt. 10 millivolt omega 1t. So it will follow the same frequency. You expect whatever input frequency your signal is, your output frequency will be the same, right? So what happened is that this is assuming that your omega 1, let's say is, I'm just going to give you an arbitrary 1 kHz. So what if I start to increase my frequency? So I'm changing to another frequency, omega 2. So I'm just going to assume that you increase your input signal with a different frequency. What happened is that I could, this is very hard to plot. Just assume that as a maybe 10-fold increase. I'm just going to using the same. Let me do the same thing. So let's say if I increase my frequency by 10-fold, it's a different time scale. So let's say if I'm increasing my input signal to a higher frequency, let's say omega, this will be 10 millivolt sine omega 2 t. So at a much higher frequency, let's say omega 2 is much, much higher than omega 1, a different frequency. What is typically being observed is that instead of having the same gain, typically you would then have something, attenuation of gain. For example, this will be my input still. The white will still be my input. The expected output at a higher frequency in most circuits will be, this 2 will simply be a low frequency, typically referred to as a low frequency gain. When you reach high frequency, you will see attenuation of gain, meaning that you might get something like this. The amplitude of the signal will be smaller, and then it will be lagging. Lagging meaning that it will follow, but the signal itself will no longer be 20. For example, it might be only, let's say this is 20, this is 10, it will be maybe 12 millivolt. I'm just giving an arbitrary number. What happens is that you will see that the overall gain VL in omega 2 versus VL, Vin, the gain, the actual gain at a different frequency will be smaller than the voltage gain we designed, which is 2 volts. It will be smaller. You will see a reduction in gain. And also you will see a lagging. We call it lagging in time. Okay, it will actually lag behind. So your signal there will be, so this will then refer to a phase. Call it the phase shift. Meaning that it will not follow precisely as the signal increases. So let's say if I increase my frequency further, what actually will happen is that, let's say omega equals to omega 3. So I was still giving a signal. This is much higher frequency. So the magnitude of my input signal is still the same. Let's say if this is my signal. The magnitude is still 10 millivolts. But then my output at a much higher frequency, this is much, much higher than omega 2, then what happens is that you will see signal maybe out of phase, at same frequency but out of phase even further, but at a much lower speed. Much lower, not speed, much lower magnitude. So it will remain the same frequency, but its magnitude, the signal VL, will be Vs Vp sine omega 3t. The frequency will still remain the same. Let's say this is my input Vin, will still be 10 millivolts sine omega 3t. So what happens is that you would then have a significant reduction. This will be smaller than your original input voltage. And then another thing is that we'll then experience another more significant phase shift, meaning that it will not follow me lagging even more, or maybe experience until 180-degree differences, maybe 180-degree delay. So we suffer a very significant delay. So it will be more lagging. And then your signal becomes much smaller than what you intended to be. Intend to be increased by 2 times, but it would then delay further down. With the same frequency, but the magnitude will be much smaller, and then a more significant delay in your signal. So how does one analyze this? One of the ways to analyze this, instead of doing this analysis in time domain, this is a time domain analysis. We're going to go to frequency domain. So the way to do this is that I have a circuit. If you want to get a frequency response of whatever circuit you have, what you actually do is that you use a spectron analyzer, which I'm going to input a signal. Let's say this is Vs as a function of Vp sine omega t. And what I'm going to do is, instead of sweeping magnitude, I'm going to sweep, let's say, a test voltage. Okay, so I'm going to sweep frequency, omega. So I'm going to sweep omega from 0 to whatever high bandwidth the circuit allows. So you start with a low frequency and sweep all the way to maybe 1 gigahertz. So what happens is that you will be able to get, so I should get, once I sweep different signal, I'm expecting to get VL as a function of frequency as well. I should be able to get this. This will then be with a magnitude and divided by the magnitude of Vs. This will then give me the voltage gain. So the voltage gain will, instead of having a constant, it will then be represented as a frequency, as a function of frequency. So this will be my transfer function, voltage gain, voltage output, the average magnitude of your output, absolute magnitude of the output, absolute magnitude of your input, divided by Vt. So this will be your Vp divided by Vt. And then this as a function of frequency. So in typical circuits, if you have simply for example, a common source amplifier with capacitive loading, what happens is that it would typically look something like this. You would then have, let's say I'm just saying that I have a typical common source amplifier like this. With some capacitive loading, a typical response will be something like this. This will be a typical response of a single-stage amplifier, meaning that you would then have this is what we talked about before. We're assuming that its gain is probably around GM or D. When frequency is low enough, when it reaches something called this is typically referred to as the corner. So once it reaches a corner frequency, it starts to ramp down as the effect of capacitance become more obvious. So then you get corner frequency, and this is what happens is that you actually be able to maintain again. This is where you can maintain. We call it the low frequency gain. Typically, when capacitive components are not effective, and it will drop off. This is called the gain roll-off. As frequency increases, this is mainly because your input is not high. At high frequency, Vout cannot reach high enough. When C low needs to be filled. The way to think about this is that the reason why you see gain rolled off, meaning that your output cannot follow input, you're seeing that, is because it takes time to charge up capacitance. So if you have capacitive components, if you have unlimited amount of current, you have maximum current, you don't actually see the response, the delay in speed. So that this is when frequency is low, you can see mostly follow. You don't see much difference. But as frequency increases, meaning that you have to charge up the capacity empty, charge on empty very fast, that meaning that your level may not be able to change as you desired. So therefore, you see this gain rolled off, especially in capacitive, when capacitive components are introduced into the circuits. Okay? So let's think about how does one construct transfer functions when we have capacitive elements. So one of the most simple way to think about this, instead of putting it into introducing transistors, we're going to simply use an RC network just to remind you as to how one analyze this type of frequency response or construct a transfer function of the circuits. So one of the way to do this, I'm going to use a simple example. So I'm going to use a RC. We're going to use an RC network and see if we can construct a frequency response curve like this. So let's say if this is a very simple, just 1R, 1C network. So this will be my input as a function of frequency. This will be my output also as a function of frequency. So to construct this, to build what we call the transfer function, by definition, it will simply be j omega, a transfer function called h j omega. If you do Fourier transform of your input and output signal, then it will be V out. Time domain, we change both of them into frequency domain. And this will then be, if I'm using simply a voltage divider, it will be R plus ZC, ZC, the impedance of a capacitor. Everyone knows that the impedance of a capacitor is j omega C. Let me just give a label so that we get. Okay? So for this capacitance, it would then introduce an impedance of j omega C. So we can actually construct our transfer function as to 1 plus, sorry, let me just do it slowly. This is R1 plus j omega C1 over j omega C1 over 1. So this transfer function would now turn it into 1 plus j omega R1 C1. So one of the ways to rewrite this is that you could actually assume let R1 C1 equals to omega 0 over 1. This is the time constant of the circuit, and the inverse of that will give you a distinctive frequency. So this will be, this can be rewritten as 1 j omega 0. Okay? So this is the transfer function. If you want to get this is a complex number, you want to get its absolute value. The voltage gain is actually, as a function of frequency, is actually the magnitude of your transfer function. So the magnitude of the transfer function will be 1 square root. This complex number, this is just math, square. Okay? So if I ask you to do the plot, what happened is that the complex number can be represented as its magnitude times exponential j theta. Theta is also a frequency, your phase. So the phase of this complex number, if you simply constructed, this will be theta. So let me write it again. So based on this particular RC network, we could get our magnitude of this transfer function, which is voltage gain, which depends on 1 plus omega 0 square. Okay? And the phase component, well then, because it's in the denominator, therefore you get 0, because the phase of the numerator is 0, and the phase of the denominator is minus tangent omega 0. So these are just complex number math of complex numbers. So once you have this, you can construct the first transfer function curve we call the Bode plot. We'll come back to the rules next time, but I'm just going to give you what it means by plotting a Bode plot. So the Bode plot simply consists of two components. If I have a transfer function, if I can use math to get my transfer function, the Bode plot contains two components against frequency. One is its gain, which is the magnitude. So this is the part of the gain, or the typically referred to as two names, magnitude of the transfer function, Okay? And then you want to also plot the phase. Your phase is the delay. It would then describe the delay. So magnitude would depend on as my frequency sweeps, how does the magnitude of my yellow signal, the signal from top, shrink as frequency increases. So the response of that will be described by the gain. And the lagging, this will then determine the signal lag. This will then give you how much lagging there is in your signal. So even though my signal is already started to move, there's a lag between the input signal and the output signal. There's a difference between these two signals. So the delay in delta t is indicated by your phase shift. Okay? So we can do the plotting now. So based on this very simple RC network, you will see that because the way to do this kind of plot, because this is typical log scale, so it moves in 10 scale. So this will be, let me label omega 0. So this is typically in log scale. Both of them in log scale. And your gain is also in log scale. Either in log scale or in dB. So the definition of dB is decibels. So definition of dB is, let me define gain. If you want to determine gain in dB, it equals to 20 log So if my gain, for a gain of 1, it will then be 0 dB. For a gain of 10, it will be 20 dB, and so on. So you get a sense as to what it means. For a gain of, I just move 100, it simply give you 40 dB. So 40 dB simply means that you have a gain of 100. Okay? So if you want to do the plot, we can actually start doing the plot. Once we have this, let's say if I'm using dB, this is instead of dB. So typically what you do is that you look at the corners. So when frequency, so you look at boundaries when frequency is much, much smaller than omega 0, what happens is that this transfer function again will actually equals to 1. This is much more smaller than 1, so what happens is that you can ignore So you can simply ignore this, so it should approach 1, sorry. So again, at very low frequency should approach 1. This is 0 dB. So you start with 0 in terms of dB, and then it will go all the way. You can actually check when this is 10 times smaller. It can barely register because if 10 times smaller is still smaller than smaller. So if still 10 times smaller, it's very close to 1 still. Only when it hits omega 0. So we look at this. This is when omega is smaller than omega 0. This we know that the gain is approaching 1. Right? But when it hits the particular point, this is the corner of the turn. So this is the turning corner. This is where we highlighted. This is referred to as the corner frequency. So the corner frequency, if you look at the second scenario when omega equals to omega 0, what happens is that the gain itself, the magnitude will then turn into square root of 2, 1 over square root of 2. So this will then give me minus 3 dB. Okay, so this is typically referred to as either the corner frequency. So you will see, let me explain that a little bit. So this will then give me minus 3. Okay, so you get the corner. So what we typically refer omega 0, in this case, as the corner frequency because it starts to turn, we'll see why, or minus 3 dB frequency because it becomes minus whatever is at is close to DC level. Its low frequency can degrade by 3 dB. So meaning that if it starts with 40 dB, it will be 37. If you start with 100, this is when we start at 0. But if you start at a gain of 100, which is 40 dB, then this will be 37. So you should be able to answer that question as to if I shift these levels. No matter what, the difference between the two is 3 dB. Okay? And then let's look at when frequency increases a lot. So when frequency increases a lot, at much higher frequency, let me use this board. So condition 3 is when omega is much larger than omega 1. Omega 0, what happens is that your overall magnitude would then be, because of the square law, you can ignore the 1, so it will be approximately omega 0. Okay? So what does this mean? This means that the gain is inverse proportional to omega, meaning that it will drop linearly if it increased by 10. So to think about this is that you could simply check 10 omega 0. So for 10 omega 0, your gain should decrease by 10 times following these rules. So from 10 to maybe even more. The turning point might be 100 omega. So these are in logs, so everyone knows. So let's say 100 times omega. So if you're looking at this high enough frequency, what happens is that you know that it will drop from here to here. It will drop tenfold. Tenfold meaning 20 dB. So this is referred to as a decay. So we know that by this equation, it tells us that the slope of the decay, the slope is minus 20 dB per decade. This simply means that the gain is inverse proportional to omega. That will give you per decade 10 times degrade. That's minus 20 dB per decade. So meaning that it will drop. I'm just going to connect that. So this was simply, what does it mean? It means that the slope, this is 10 times, and this is 20 dB. Okay? If your frequency increased by tenfold, the gain decreased by 20 dB. That's 10 times. So that's inverse proportional to 1 over omega. It's inverse proportional to omega. That's what you get. So that will give you a slope of minus 20 dB per decade. So once you go through an example, so you get a sense as to the Bode rules. We're going to come back to the Bode rules on Thursday. But just to give you a sense as to how does one construct this plot by finding extreme points, like very low frequency, very high frequency, and then the connecting transitional point. This is very much like when we do transfer curve of a diode circuit. You look at extreme borders and then see what happens when it meets in the middle. the transition points. You find the transition point, you find extreme levels and then transition points to connect the whole plot. So we still have a little time. Let's look at the phase component. So we'll simply go back to the math. So we know that the phase will be simply minus tangent omega 0, arctangent, minus arctangent omega 0. So also you look at very low frequency and very high frequency. So very low frequency, this is 0, meaning that your tangent is 0, the phase is 0. So at very low frequency, and when it turns, so we find out each point. So at very high frequency, let me write it down. So you also look at 3 regimes at omega close to 0. What happens is that the phase shift is 0, meaning that frequency is very low. There's no lagging. At very high frequency, what happens is that your phase at very high frequency, this equals to minus arctangent infinite. This will give you 90 degree. Arctangent infinite is minus 90, so plus and minus sign. So you know that it goes to minus 90. And then let's see the transition point. At omega equals to omega 0, this will be your, based on the math, the phase will simply be minus tangent arc 1, which is minus 45. OK? So if you want to plot the phase component, it will look mostly flat, and then it will start to drop a little bit to 45, and then all the way to 90. Minus 90. And at this particular point is minus 45. So that's how you describe the amount of lagging in the system. This will be simply delta t. In time domain, this delta t over t is theta over 2 pi. So the amount of delay in phase will refer to as the delay in time domain from the 2 signal. OK? So you need to be aware of having this delay will then, having these capacitive components will then lead to a scale in your magnitude of your signal, because we know that it needs time to charge up the capacitance. Once frequency increases, you may not reach the peak level that is desired when it's reached infinite. So there's a lagging in time and also a reducing of magnitude. Both would construct to a change in your signal between input and output. So to describe the full input and output response, it will then take both the gain, the change in gain, and also the transfer function in gain, and also the transfer function in phase. But I believe in the textbook, in chapter 11, it limited mostly on the gain side. We were not going to talk about delay, because delay will mostly lead to feedback problems. So I'm just going to talk about phase shift here. But in the rest of this chapter, I'm going to limit the discussion on only the gain part, because we probably won't have time to dig in too much into the impact of delay. It will lead to mostly instability in feedback system, which will be discussed in chapter 12 when you take advanced courses. OK? So 我稍微简单讲一下，就是说我们在做这些频率响应的时候呢，通常我们要真的观察，就是它会有2个结果。你如果看这个 time domain 的讯号的话，就是它的讯号会比预期的来得更低，就是在低频的时候的讯号比较高，高频通常会比较低。这个 high pass filter 都会是这样的，或者是说像我们刚才做这个 high pass filter， 或是任何你有 capacitive load 在电路上面，通常大部分都长这样，大部分的电路都比较像这样。那除非你特殊设计什么 filter 啊那些东西，但是正常的情况下都是 就是 low pass filter， 就是低频的可以过，然后高频的会被滤掉。那滤掉的原因就是你要冲这些电容要花时间，所以它没有办法达到那个 level， 所以你会看到它的 magnitude 会变降低，不如你预期设计的 level。另外一个事情就是它会有个时间的 delay。那 phase delay 呢，那就会造成你会讯号 input 跟 output 中间会有个时间差嘛。那这个时间差呢，在我们在这个课至少课本上的11章比较没有在讨论哦，所以它会到频率，因为通常这个时间差会导致你的讯号呢会有一个不稳定的问题，特别在回授系统。如果你不做回授系统是没有差哈，但是如果你有回授系统的时候，你的回授就会 delay， 就是变成说你本来回授是及时的嘛，如果你回授来不及，就会导致那叫什么？你要校正回归，就你会导致一个 delay， 那造成一些错误，就是你 input 如果是错误的话，造成后面 feedback 的错误，所以会造成 instability 的问题。那课本呢是到第12章才讨论的。那我这边只是稍微讲一下，通常你真的要 describe 你整个讯号的变化，就是同时要 gain 跟 phase， 但是11章我们会尽量只讨论 phase 的 component，gain 的 component，phase 的 component 呢，我们就等到未来大家上更 advanced 课程之后呢，再讨论。所以我们今天就先讲到这边，就是给大家一个简单的 overview as to 频率响应是怎么一回事，然后怎么去讨论它，讨论的工具就是像这个。